Hello, everybody. Welcome to the workshop on how to approach STEP questions. What we're looking at today is how to approach STEP questions. And after I do a quick intro to us, I'm going to tell you why we chose this as the topic of today's workshop. So essentially, I'm just going to introduce a few of us here. Just want to check, I think we might not have Marla with us right now, but my name is P.R.O.F. I'm the first person here that you see. I am the founder here at the Oxbridge Formula. I personally studied maths at Oxford, but when I was in sixth form, I think back then, which was quite a number of years ago, it wasn't very usual for people to actually want to do STEP papers. And I approached my examinations officer and said, please can I enter myself a STEP? It wasn't a normal thing to do back then. I really loved the STEP papers, and we started STEP maths after I finished uni, after I'd been a teacher for several years teaching maths, because I felt like it's such a difficult exam and there isn't necessarily that many resources out there. I think the number of resources maybe have slightly increased, but really there was nothing in depth just focusing on STEP. So I started this with Chris. Chris is our lead tutor here and head of education here at the Oxbridge Formula. He also has a first class degree, master's degree in maths from Oxford. But also extremely good at STEP paper. You know, he didn't go to Cambridge, but like very, very, very good at explaining STEP questions, doing STEP questions. So we started what was then called STEP Maths. And over the years, we've added more subjects, and now we're called the Oxbridge Formula. But if you've seen our website, you know that the old one still exists, and it's called stepmaths.co.uk. We're also going to be joined at some point by Marla. And Ben, can we just message her to make sure that she has got the link for today? Marla is one of our former students. She joined our program last year, so she's going to be joining us and speaking to us for a bit. We've also got Isaac here. Isaac is one of our STEP tutors. He's currently a student at Cambridge. Just give everyone a wave. You don't need to introduce yourself, but yeah, okay. And you know what? People might not be able to see you. If you just say hi, that would be great.
Hi.
Okay, perfect. And then Chris, if you can just say hi, because I introduced you, but people might not be able to see you.
Okay, hello everyone.
Okay, perfect. And then we also are being joined by Adam. Sorry, Adam, I don't have your picture on here, but Adam is one of our other STEP tutors, and he's also currently a student at Cambridge, correct? Yes, okay,
yeah.
Very good. So studying maths, so all of them have, successfully passed the STEP papers with really, really good grades. In fact, Isaac, what were your grades in STEP, if you don't mind sharing?
S.
Okay, wow, amazing. Okay, so that's SS in step 2 and step 3. Adam, what were yours?
I got 1-1.
Okay, excellent. Still like very good. And we're going to see later on like how hard it is to get these kind of grades. So congratulations on those amazing grades. So let's have a quick look. So these, just very quickly, are some students who have worked with us and have successfully gotten into Oxbridge. And what is our goal, right? If you're here and you're thinking of doing a STEP paper, you are going to be good at maths, right? It's not that you struggle with the material. It's not that the A-level content is hard for you. It's also not that when you know what you're doing, you're like struggling with the actual maths. Like the algebra normally isn't really a problem for people. What people mostly struggle with, and we found this by working with hundreds of students over the years, is simply like seeing what to do when you have such an unfamiliar or unguided problem. So it's, how do I get started? How do I approach this problem? That's what most people have the most trouble with. And therefore, our goal in working with our students is to teach students how to approach these problems, how to actually know how to get started with them, and to make progress with the problems regularly. So a workshop is going to be in 2 parts. Firstly, we're going to be talking about logistics. So what is STEP? When is it taken? Who asked for it and how is it used? And how does it differ from A-level? Now, if you're a year 13 student, you probably know a lot of this stuff already. So we're going to go through it quite quickly. But I think it's also quite important for you to understand how difficult it is and so on and so forth. Then the second thing we're going to be going through is our approach. This workshop is called How to Approach STEP Problems. And we have this approach called P.R.O.F, P.R.O.F, and we'll be going through what that means later on. So it's our P.R.O.F methodology for tackling STEP questions, how to dissect a question. We're going to be looking at exam technique. So how should you time your questions? How do you choose your questions? How do you check? And then we're going to be looking at preparing to sit STEP. So what are good study techniques? What kind of timetable should you be using? So preparing to sit STEP in 2023, which is year 12, and preparing to sit STEP in 2022, which is year 13 students. And very quickly, just for your information, if you are currently a year 12 student, then you will submit your UCAS application in the middle of October. Before that, you write your personal statement, and you might do preparation for other admissions tests. And then you'll have your interview in December. Now, if you are applying for, say, Cambridge Maths, you'll get offers made in January, and they will be dependent on you getting specific grades in your step papers. If you apply for something like Imperial Computer Science, they've already, some of them made their offers in December already, and a lot of them have been dependent on getting grades in step 2 or step 3. You might also start your A-level prep early, so you might want to do some step 1 preparation throughout year 12, and then move on to step 2 and step 3 preparation next year, and also attend open days. Now, how does this correlate to what we might teach you? We've got step 1. If you join our program, which I'll talk about a little bit more in a second, we start preparing you for step 1 in math kind of until December this year. That's using our online resources, workshops, and tuition. And then next year, we'll give you access to, so this is in 2013, for the people who are currently in 12, year 13, we'd give you access to the step 2 and 3 resources and tuition, and we've got a whole program there. And also for year 12 students, we've got summer schools and admissions test courses, as well as group interview courses and mock interview courses. Now, for year 13, we'd give you online resources now, so the step 2 and 3 resources now. We also run fortnightly workshops, or actually they're weekly workshops, where we kind of incorporate these P.R.O.F that we're going to be teaching you today into our sessions, and also mini timed mocks, because we do find that when students get into the real exam, a lot of people who mess up on the day, it's just like the nerves of the exam kind of like got me. So what we're going to try and do is prepare you with mini mocks throughout. And in between, we'll have live courses and so on. And if you do get one-to-one tuition, that starts immediately and will finish when you do your step exams. So I don't really want to kind of focus too much on that, but that's kind of a timetable. So what are the step papers? Well, they are firstly taken at the end of year 13, typically after your A-levels, you're all at the same time as A-levels, and importantly, after offers. Now, a lot of people will be here with an offer that they got from Cambridge yesterday, which is fantastic. Congratulations if you got an offer involving STEP. But the important point to note for year 12 students is, unlike basically any other degree course, getting an offer in January from Cambridge for maths and or Imperial doesn't mean that you've got in. You then have to, your offer will be contingent on you getting a specific grade in STEP in order for you to kind of get in. There used to be 3 papers, step 1, step 2, and step 3. Step 1 was scrapped during the pandemic, but step 2 and step 3 still exist, which means it has become a little bit harder. A lot of universities would say, you can, if you get a grade 2 in any of the step papers, then we'll let you in. But now step 1, the easier one, doesn't exist. So the easiest quote unquote thing you can do is step 2. So it has made it a bit more challenging. It's a 3-hour paper, and you get 12 questions per paper, and you do a maximum of 6. And the questions are split between pure maths, mechanics, and stats. If you don't study one of those to a great amount of depth, it doesn't matter. Like, there are 8 pure questions. So you can do all pure, or you could do pure and some mechanics, or you could do pure and some statistics, or you could do, I think you could get away with doing all mechanics and statistics if you really, really wanted to. But I wouldn't recommend it. I don't think most people do that. Every question is worth 20 marks, and all questions are weighted equally. And they're graded S1, 2, S1, 2, 3, and U. S is the highest grade, which is like a distinction, and U is ungraded, the lowest grade. Now, where is the material taken from? So step 2 takes material from A-level maths and AS further maths. Step 3 takes material from A-level maths and A-level maths and A-level further maths. And important to note is that just being good at your A-levels isn't enough. STEP is very much aimed at the top 2% of A-level mathematicians. And why do they have these papers? You might be thinking, well, okay, but A-level's hard enough. Actually, to be selected for a tough degree with a mathematical high amount of mathematical content, it probably isn't enough just to be good at your maths and further maths. They are wanting to test that you can think like an undergraduate, that you would succeed in an undergraduate degree. And when they have, when they've created these papers, they've then, and by the way, the STEP is the same age as me. It was in the 80s that it was introduced. So they've obviously refined this test to correlate with success in a maths-based degree or in a maths degree at Cambridge, and therefore equivalently any quantitative degree out there. So they've seen, okay, how do people do in the STEP paper? How do they do at the end of a 3-year course at Cambridge? And they've adjusted the paper to make sure that the test picks the people who are most likely to succeed. And when you look at the STEP questions, you'll see that they are like, well, you might not see this because you haven't seen a university paper before, maybe, but they're like university style questions, except that they're using A-level content. So they are basically A, checking that you're a good candidate for a highly quantitative degree, but B, they're also preparing you for the degree. I think Stephen Siklos, who is like the chief examiner for STEP for a long time, he actually says something about how STEP was designed to prepare you for a tough maths degree. So what would a typical maths offer be? So at Cambridge, you will typically be asked for grade 1 in both step 2 and step 3, but often you're asked for grade S's, and we have heard of numerous students being asked to get SS. At Imperial, it can be variable, but often they're asked for grade 2 in either step 2 and or step 3. That's frequently for computer science as well. Warwick, Bath, UCL, etc. They might ask for grade 2 in either step 2 or step 3, but that's for a reduced A-level offer. So you can get away with not doing the STEP papers, but often it makes sense in case maybe one of your A-levels isn't as good as it could be on the day. And how are STEP grade boundaries determined? Now, the interesting thing here is that Cambridge picks, whether or not you're applying to Cambridge, Cambridge picks the grade boundaries for STEP based on their cohort of students. So what they typically do is make 500-ish offers, and we're going to see a graph of that in a second, but there are only around 250 places for Cambridge mathematicians. So what they're doing when they pick their boundaries is they are wanting to select the top 250 people, and they're going to make sure that the end of the grade 1 boundary, more or less between step 2 and step 3, picks the top 250 people. Okay. Now that means that if you are not applying to Cambridge, you're still going to be kind of measured against the same benchmark as the mathematicians who have Cambridge offers. So that's kind of important to bear in mind. And when they are picking people for Cambridge, the step 3 grade takes priority over step 2. So if you just missed your step 2 offer, so you've got like 1 mark off, and we know a couple of students who are 1 mark off a grade 1, but they did really well, they got a high 1 in their step 3, they would still be accepted. I'm not saying that you should aim not to get the grades that have been asked of you. I'm just saying that step 3 takes like a lot more priority, but obviously it's a lot harder as well. And yeah, as I said, applicants at other universities are judged relative to Cambridge candidates. So I guess what we're trying to say here is, look, actually for maths, the number of applicants is more or less consistent. You know, it hasn't changed massively, but equally, nor has number of places. Like, it's very consistent in terms of how many offers they give out every year. And it's also pretty consistent in terms of how many people get a place. So if a lot of people do really well in the step, it doesn't mean that more people are getting in. It just means that they're going to increase the grade boundaries, so the same number of people get in. So what I'm trying to emphasize to you is STEP is a competitive exam. You are literally competing against everyone else doing STEP in order to make sure you're within the top X%. And let's have a quick look at what that percent is. Oh, before we do that, let's look at, this is quite a hard step 2 paper. But in this particular year, you had to get 100 out of 120 to get an S. This must have mean it was a relatively easy paper, I would say, because the grade boundaries can be lower than this. For grade 1, you had to get around 80, and for grade 2, you had to get around 70. So remember, if you're applying to Cambridge, you want to kind of aim for about 80 in step 2. It's a little bit lower in step 3. And if you're applying to another university and you need a grade 2 in any step paper, and you happen to take step 2, you're still aiming for a good 70 marks. And we'll go into how, remember that every question is worth 20 marks. So what's this? We're looking at about 3.5 questions that you've got to get perfect. So I would aim for like 4 very good questions to get that. Somebody's asking what the total mark is. Well, that's a good question. So you have 20 marks per question, and you're allowed to answer up to 6. So the maximum mark you could get is 120. As you can see here, somebody's got 119, amazing. Actually do know quite a lot of people who've got like full marks in step 1, which is kind of crazy. But yeah, But you can see for Cambridge, even if you answered 4 perfect, if you answered 4 questions perfectly, you could still get in. So often there isn't time to do all 6 questions, and aiming to do 4 really good ones and one extra one could be enough to get you in if you were asked for a grade 1 at Cambridge. So, okay, let's look at how hard step 2 is. Okay, so remember we said we have all of the A-level mathematicians, and 2% of them is what step is aimed at. Step is aimed at the top 2% of A-level mathematicians. Within that 2%, 6% typically get a grade S, 16% grade 1, 17% grade 2, 44% grade 3, 18% don't manage to pass, unfortunately. But yeah, look, to get grade 2 or above, how much is that? Around 40% of people would get a grade 2 or above in step 2. Looking then at step 3, by the way, Chris, feel free to butt in if I'm missing anything. Again, now we're probably looking at close to 1% of A-level candidates actually maybe ever sitting step 3. It's a little bit more generous because actually the majority of people sitting step 3 will be Cambridge. And remember, Cambridge want to get 50% of their people in. So, but there will be other people doing step 3 as well. So around, what's this, 33% of people will get a grade 1 or higher. And below that, we've got your grade 2, grade 3, and grade U percentages here. So yeah, it's pretty tough, and you are competing against the Cambridge mathematicians. I'll just emphasize that. So what we want to look at now is how do A-level questions differ from STEP? And if you're in year 13, bear with us. We're going to go right into the P.R.O.F methodology after this. So Chris, tell us, how would you say that A-level questions and STEP questions differ?
Okay, just very quickly for comparison, we've got a couple of questions on quadratics, one from A-level, one on STEPs, we can compare. Well, you can see the A-level question here. Firstly, they give it a real world context. They say it's about modeling the profit of a company that make toys. They give you a graph, you don't have to draw your own. They tell you, if you look at the instruction words in the question, kind of on the right-hand side there, part A is explain why, and then they're telling you £50 isn't a sensible price. Part B is find a value, so you're just doing a calculation. Part C, you're just reading off 2 other values. So it's very precise as to what you need to do. They're giving you a lot of guidance. Also, the question is very numerical. You can see the equation by the graph. It's got specific numbers in. There are specific prices throughout the rest of the question. And also, if you look at the very right-hand side, it's a little bit faint, but they tell you how many marks each part is worth. So you can see, okay, where do I need to spend my time? You can kind of plan your question that way. So if you compare to STEP, it's kind of the opposite on all those points. So here we've got another question, which is about quadratics. But so firstly, there's no real world context. There's no picture drawn for you. It's highly abstract. There aren't even many numbers. You can see the very first line is defining 4 constants. And then we just use constants all the way through. You have to draw your own graphs. If we look at the instruction words again, in the first line, it says show that. And then you need to know what a sufficient condition is. The next line, it says determine whether. Part 2 is determine necessary and sufficient conditions. So again, you need to know what that means. But the point is, these are kind of proof type instructions. So you're not calculating something, you're constructing proofs. And also there's much less guidance as to what you have to do. It's not like show this price is not a viable one for the company. It's you've got to determine what the conditions are. We're not telling you, you've got to figure it out yourself and then prove it. And likewise in part 3, it says what can be deduced. It's completely up to you to interpret that. And finally, although you know the whole thing is out of 20 marks, because all STEP questions are 20 marks, you don't know how those marks are distributed. So you have to think very hard about what are the most difficult parts of the question going to be, and how much time should you be expected to spend on each part.
Okay, yeah, brilliant. So think about when you're at school, right? You might write essays. Now, when you're writing an essay, you're always told, I'm pretty sure your teacher would have told you to write an essay plan, but nobody ever tells you to sort of step back from a maths problem and actually plan. So the P in our P.R.O.F methodology is problem planning, right? So it's like essay planning, but it's for maths problems. Before you write an essay, you make a little plan so that you know what you're going to write before you start writing. And similarly here, we're going to be teaching you problem planning, which is how can you plan what you're going to do in every part of the problem, or as much as possible. Okay, it's not the same as an essay, we know exactly what you're going to write, but you can have a good idea of what you're going to do at every part of the question before you actually put pen to paper. So that's kind of something that's really, really important. We found stepping back and thinking. What do you do when you're problem planning? Well, first thing you want to ask yourself is, well, what is this problem actually asking me? What is it really asking? Because there's just the words. If you just look at the words, okay, this is what it's asking. And then there's like, let me think about it a bit further. Ah, that's what they're really getting at. And then another really, really important one in STEP is that more often than not, like most of the time, the different parts of the questions relate to each other. And if you can see the links between the parts of the questions before you actually start doing the question, you're going to be in a much, 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 much better position to actually successfully solve the problem. So part of problem planning is seeing the links between the questions. And lastly, understanding the logical route through the problem and not kind of being, I remember when I was doing STEP questions, I'd feel quite blind. Like it's like you're going through like a dark forest. You don't know where you're going next. Like I'd just be writing, okay, hopefully the next line works out. Hopefully it works out. But I didn't know where I was going. I didn't know what I was aiming for. So part of the problem planning is just to give you a route through the whole problem. So what we've got is we've got this STEP question now. Even if you are going to be doing step 2 and step 3, don't despair. The point we've chosen a step 1 question because we knew a lot of year 12 students signed up, and we didn't want to give them a topic which was completely like out of their depth in terms of something that they'd never seen before. What we're trying to demonstrate with this question isn't like how to solve this particular question. It's more about what are our thought processes, and the same thought processes and logic could very well apply to a step 2 or step 3 question, but we just wanted to show you our way of thinking through the problem. So I'm going to hand over to Chris to do this bit, and Chris, just let me know when you want to see the next part of the slide.
Yeah, absolutely. Well, as the question at the top there says, we asked what's the key ideas we see. We're going to think about what we see as we read through the question, and also what we kind of might annotate or at least make mental notes on. Pavel, would you like me to read through the question first?
Yeah, well, actually, I think that would be a good idea because there were a few people who said they hadn't seen it. So if we can read through it quickly, and then what we'll do is ask the students for their opinions on what key ideas they saw. Yeah. Okay.
So if I start reading, it says, if you don't mind following along with the cursor panel.
Yeah, absolutely.
It says the function f of x is defined when mod x is less than a fifth, and it's defined by this this sum. So we've got a sum to infinity, and the terms are all of the form an, so that's just going to be some number times a power of x, x to the n. So we've got all these coefficients an, and it talks about those in the next line. It says a0 is 2, a1 is 7, and then we're given a recurrence relationship for an in terms of an minus 1 and an minus 2, and that holds for n greater than or equal to 2. And then we start getting to the instructions. So this often happens in STEP. They define something, and then you have to start doing things. So it says simplify f of x minus 7x f of x plus 10x squared f of x. Hence show that f of x is equal to this sum of two fractions, 1 over 1 minus 2x plus 1 over 1 minus 5x. And then the last line, hence show that an equals 2 to the n plus 5 to the n. I think we're meant to read that as for all n. And then there's a part 2, but it does look very similar. So very quickly it says g of x is defined for mod x less than a third by a similar sum, just with bn instead of an. And then we're given some values. b0 is 5, b1 is 10, b2 is 40, b3 is 100. We've got a recurrence relationship. Bn is p times bn minus 1 plus q times bn minus 2. We're asked to find an expression for g of x as the sum of two algebraic fractions and determine bn in terms of n.
Okay, good. So now that we know what the question is, hopefully you all had it, well, most of you did have a chance to look at this beforehand. So can you put in the chat to us, what were the key ideas that you saw in the question? What were the key things that you thought would be good things to try in this? Somebody says, my first guess is to identify a couple of values of a and to express the expressions to simplify as the sums. And to express the expression, to simplify the sums. Somebody says factorizing f of x. Factorize the quadratic. Okay, so maybe you spotted a quadratic here and you want to factorize that. Okay. Somebody says maybe write out the summation. So maybe you want to write a few terms of this out. Okay, anything else? Give up, lol. Okay, don't give up. You could do RA. What do you mean by RA? Reverse argument. Okay. Be aware of the restriction on x. Okay, very good. So this is a really good thing to be aware of. Find out, what did somebody say? They said, find out why less than a fifth. I'm not sure what you mean by that, actually. Chris, do you know? Oh, okay, wait, sorry. Yeah, why have they said that this has to be less than a fifth? That's really good. F of x is shown as two convergent geometric series, somebody says. So we can write out the expressions of the series and look at alternating terms. Skip to the end of the paper. Replacing an with its definition, then maybe you can set the sum from a different starting point. So are you saying maybe kind of sub this expression into here? I think maybe is what is being said. Okay, then the 7 and 10 appear in the an expression as well. Ah, that's really nice. Okay, so you've spotted that the 7 and 10 are here and they're here, but they're opposite signs. But really good to have spotted that. I think that's definitely going to be an important thing coming up. So it says it looks like they'll cancel because they have the same numbers but different signs. Somebody says for part 2, representing f of x with a0 and a1. So for part 2, maybe you mean this bit, representing f of x with a0 and a1. Not sure exactly what you mean by that. Recognize that an definition has same numbers as what you're trying to simplify. Yeah, true. Use what you have to show and see what route you have to take. Ooh, I like that. Recognize the name of this person as well. So you have, you know that you're trying to show this. So maybe that will help me determine how I'm going to show it. Very good, like it. Test the summation by subbing in some values to see if a pattern emerges. Okay, so maybe I think it sounds like what you're saying is write out a few terms and see if a pattern emerges. Yeah, that could be a good way. Write out the first few terms, make comparisons to the second question to spot the scaffolding. I like that. So compare what you did in part 1 to what you're being asked to do in part 2. Replace f of x with the sum. Look for what cancels out. Okay, there's lots. Use method of differences, somebody's saying, potentially. Yeah, it could work. If we can find some differences somewhere, then yes, that would work. All right, okay, somebody says they were here last year. Okay, I was like, I really recognize that name. Okay, perfect. So, Chris, let me leave it in your capable hands to tell us how you thought about this problem without writing anything, without writing down any work, just writing down key facts.
Okay. So I think first, I might just identify some things I want to underline and keep in the back of my mind. So first of all, this mod x is less than a fifth. A lot of you pointed that out. One reason to underline that is just that it's very easy to forget that kind of condition. It happens right at the beginning, but sometimes it's important. So I'll just underline it so I don't forget. And then I'll start looking at some instruction words, because that tells you what the route through the question is going to be. So the first one is simplify, but a simplified expression. And simplify normally means something algebraic is happening. So I'm expecting this to be some algebra involved. It doesn't tell you how to do it apart from that though. And the next part, it says hence show. Okay, it says hence, and therefore we're meant to use the simplification we've just done. So we're meant to get this second expression for f of x from the whatever we just did when we were simplifying. And then after that, we got hence show again. So we're meant to get this expression for an from the previous expression for f of x, the 1 over 1 minus 2x plus 1 over 1 minus 5x. So we know those have to be related. So, okay, we've now identified those things, we can start maybe brainstorming a little bit what might be relevant. So when you see a sum, Here's a little brainstorm you might do. First of all, think, okay, is this a sum I know? In particular, is it, I mean, the main kind of sum you can recognize by eye is geometric series. Is this going to be geometric? There's no reason to think so.
Can I just get a quick, can I just get a quick kind of message in the chat? Have you seen geometric series before? Just give me a yes or a no. Yes, we've seen it. No, I've never heard of it. Okay. A lot of yeses, a couple of no's, but mostly yeses. So if you haven't seen this, don't worry too much. Go away and look at it afterwards. But just bear with us for the time being. Okay.
Yeah, I mean, for the sake of talking through this plan, it doesn't really matter. The point is, does it look like a kind of sum you know about from school? By the time you're taking step, you will have seen some kinds of sum. This isn't one of them. So, okay, next thing you might think about is, if you start writing out terms, can that help? That is something that's worth thinking about. In this particular question, the numbers start to get a bit big, but you can try that at the beginning to see if it gives you any ideas. And the other thing about sums is often it's possible to kind of split up and combine sums. I think a couple of people mentioned this in what they thought about. For instance, if you substitute in the next line that expression for an, you've then got a difference of two other terms. Maybe that means you can split the sum into two things. That is one way of approaching this question. So that's a useful thing to think about when you see sums. What else do I notice in this question? Well, if we go to the very first thing we asked to simplify, this f of x minus 7x f of x plus 10x squared f of x. It's not really unusual how they've written that, because they haven't factored out the f of x, which is it's a more natural way to write it as a quadratic times f of x, because all the terms have f of x in. And they've left it unfactorized. So that's probably on purpose. So probably it's, rather than either factorizing it now or trying to treat it as one big long thing that you're trying to reason about, it's probably a good idea to look at the three parts. One way to do the question, at least, will be to look at the three parts individually and then do the sum, then add them up. So our f of x, 7x f of x and 10x squared f of x, write expressions to them individually and then try and add them up and see what happens. It also, as a couple of people noticed, if you just click to bring up the next project. But yeah, we do have this kind of numerical coincidence that the previous line we have an is 7 an minus 1 minus 10 an minus 2, so we've got that 7 and 10. Next line we've got a minus 7x and a plus 10x squared. It's probably not a coincidence, no. How can we make that similarity even closer? Well, the recurrence relationship, we have a plus 7 and a minus 10 for the coefficients. And the quadratic, we have a minus 7x and a plus 10x squared. But if we rearrange the recurrence relationship, or at least this is one way to think about it, if you move the 7 and the 10 to the other side, you'll have an, and that's got a coefficient of 1. Then you've got a minus 7 and a plus 10 for the other coefficients. And that's exactly the same as the coefficients of the quadratics. And now you can see, okay, there's almost certainly a connection. So it means you're probably going to want to use the recurrence relationship when you're simplifying. Finally, we'll just think about the two hences. So from the simplification, we're meant to get to an expression for f of x. Since we just said that the thing we're asked to simplify, you can factor out the f of x. Probably once it's simplified, you can just divide by whatever it's like. It's going to be f of x times something, divide by whatever it's times by, and hopefully it rearranges to the right thing. So I wouldn't think too much about what's going to happen in the algebra. I just hope that's going to work for the sake of planning. The next hence is a bit more interesting. We're asked to find out something about the nth coefficient an. We're meant to find an explicit formula for it. Another kind of numerical, not really coincidence, but a numerical match. We've got a 2 and a 5. We've got two terms, a 2 and then a 5. The previous line has a 1 minus 2x and a 1 minus 5x. Almost certainly they correspond 1 to 1. And we need to think about, so if we're asked about the coefficients, let's remind ourselves what that means. These are coefficients in an infinite sum for f of x, or what you might know as a power series. So how do we get an infinite sum from something that looks like the previous line? Well, some of you mentioned this in the chat. Those can be turned into expressions for geometric sums to infinity. Following a formula you should have seen before, if we just bring this up. So if you haven't seen these at school, don't worry about it, you will do. But we have this formula A over 1 minus R, where A and R are constants that define our geometric series. And we can write each of the terms in f of x that way. And therefore we can turn them back into infinite sums, and then we can read off the coefficients. So that's how I expect that bit to work. If we then very quickly think about part two.
Somebody just brought up another point, which is, okay, well, how do we get from here to here? Well, they're noticing that if you have 1 minus 7x plus 10x squared, that's going to factorize to 1 minus 2x times 1 minus 5x. And so that could be some kind of coincidence, not coincidence, but that kind of links these two parts.
Yeah, you can see in advance that that's going to work. And as people mentioned, you can actually work in reverse and see what you need to get for the simplification in order for the next part to give you the answer it says. So you can work backwards, but because it says hence, you do need to do the simplification. When you actually write out your solution, you need to do the simplification first, but you can work backwards to check your answer. If we quickly look at part two, I think people mentioned in the chat, it's similar to part one. That's always something to look for, especially in STEP. They love doing this thing where part one, they lead you through this kind of calculation step by step. And in part two, they just say, here's a slightly different example, do it all on your own. And that's exactly what's happening here. 7 had like 3 instructions, simplify, hence show, hence show. Part 2 just says you've got to obtain expression for g of x and then determine the coefficients being. So there's less guidance. So when step questions like this, where the second part is similar to the first, or a later part is similar to a previous part, it's good to think about what's similar and what's changed. So if we just read through the question and look at what's similar and what's different, we still have, this is undefined for mod x less than a third. By the way, in the previous part, we saw, they said f of x is defined for mod x less than a fifth. And again, if you've seen geometric series at school, now you can see why, because we know f of x, we write it as the sum of 2 geometric series. And the condition for them to, for the series to actually be valid is that mod x is less than a fifth. Not going into too many details. So in particular, because mod x is less than a third here, we might expect to have a 3 floating around in our answer for g of x. Like f of x was, part of it involved 1 over 1 minus 5x. So here we might expect a 1 over 1 minus 3x or 1 plus 1 over 1 plus 3x or something like that. In the remainder, we're thinking about what's similar and what's different. So, but actually, first I should just say we just to clarify the language. It says we want the sum of 2 algebraic fractions. If you just bring up the underlining, so you do need to know what that means. It just means in the similar form to f of x in part 1. So an algebraic fraction is just one polynomial function over another. And like 1 over 1 minus 2x counts, for instance. So it's meant to have a form similar to f of x. And it says determine bn in terms of n. So we're expecting to get probably something like the formula for an, just maybe with different numbers. So maybe something with some powers. And then if we think about what's similar to part 1 and what's changed, well, I mean, the whole thing looks very similar. The main thing that's changed is if we look at the definition of b, of the coefficients at b0, b1, b2, etc. Firstly, they give us 4 values now instead of just the first 2. And secondly, in the recurrence relationship, there's no numbers, just letters. So they've got this p and this q, which are mentioned nowhere else. And we somehow got to cope with this. So there's 2 things that can happen from there. Either you might be expected to have p and q in your answer. It doesn't say you will, it doesn't say you won't. But the other thing that can happen is you have to somehow eliminate p and q, i.e. find values for them in the course of the question. And if we think that's a possibility, then it starts to make sense why we might be given 4 values for B0, B1, B2, B3 instead of just the first 2, because we can use those to help us find P and Q. Because our recurrence relationship is defined for n greater than or equal to 2, so we can plug in B2 and B3. Yeah, and as someone says in the chat, we get simultaneous equations for P and Q. So you're always looking out for, like, what they tend to do is they'll teach you how to do something in part 1, and in part 2 they make more difficult somehow. You've got to spot how it's more difficult and then how to get around that. And here they've just kind of put this one more obstacle in your way that you have to work out the coefficients in the recurrence relationship. The other thing you need to do yourself is they tell you to find g of x as a sum of 2 algebraic fractions. That's like our f of x equals 1 over 1 minus 2x, etc. They ask you to determine Bn. That's like the last step, an equals 2 to the n plus 5 to the n. They haven't mentioned anything like the simplify f of x times a quadratic step. But because that happened in part 1, we can expect we actually have to do that in part 2. So that's the other way part 2 is more difficult. You have to kind of supply that step yourself. You've got to figure out what the right quadratic is. But you can probably do that by comparison with the first part, because we saw this connection between the coefficients in the recurrence relationship and in the quadratic. We expect the same thing to happen in the second part as in the first. So, okay, I've kind of talked through my planning there. Some of this is stuff you do on paper, like underlining and maybe a little bit of brainstorming. But some of this is things you do in your head while you're thinking about the question. And you could do this quite fast once you've practiced it.
I think the other reason why this is so important is because if you can quickly plan a question in 5 minutes, you can actually decide, because in STEP you have a choice. You've got 12 or 13 questions and you only have to do 4 or 5 or 6 of them. So is this a question I can actually see a route through? And if you can, then you might as well do the question. But if you can't do this easily and quickly for a question, you might be one that you wait until you decide whether to do it or not later. So at least you can find the questions you can plan quickly and choose those easily.
Yeah, so I think we just want to summarize our thought process quickly. So what did we do? First, we did some looking at the instruction words and the links between parts. So basically, that's kind of the structure of the question. We brainstormed some things for the kind of key, one of the key concepts, which is sums, because there's a few things we know how to do with sums, so we can quickly bring those to mind.
What were they, Chris? Just remind me.
We said, firstly, is it a known kind of sum? Secondly, does it help writing out any terms? And third, can you split it up or combine sums together somehow? Then we went through looking for clues here in the numbers. So are there any seeming coincidences like the 7 and 10 coming up, the 2 and the 5 coming up in subsequent lines? Maybe the mod x is less than the 5th, mod x is less than the 3rd. Those kinds of clues. And then just going through the actual steps we did it in the order they said. So we simplify, there we used our idea of, one way to think about this is you're kind of splitting or combining sums using the recurrence relationship. Then the next part is the show that. So, okay, we said we're going to divide through to get f of x as the subject, and hopefully that will simplify to this sum of 2 fractions. We identified that we want to go to the next bit where there's powers. So we'll use the geometric series formula to help us do that. And then we get on to part 2. So firstly, we just compare them, like what's similar and what's different. Here, the similarities more obvious than in some other questions, but you can often look for what's similar and what's different. We saw this P and this Q kind of stick out a bit compared to part 1. So what can we do with them? Well, we can actually just find out what they are numerically. So that's something we can do first. And then we've got the 2 steps. We've got to kind of figure out the quadratic we want to multiply by, and then find the expression for G in the same way as we found for F in the first part. If you could bring up the next 2 steps. And then, oh, sorry, just 1 step. And then we just basically follow the same steps from part 1. So once we've identified the quadratic we want to multiply g of x by, then we just follow the same steps as we did in part 1.
Okay, perfect. So that was really good for problem planning. Is there any more to say on that?
I was just going to say, I think someone asked, like, do you do this for every question? A good approach is to do a quick plan. Maybe the first sort of 3 parts of this flowchart when you're just reading the paper. So think about the structure. Then is it a topic where you can brainstorm ideas easily? And can you see any clues in the question? And can you see any links between parts? And then you can get into the details more when you actually decide to do the question and start attempting it. You don't want to plan in too much detail every question, because that's going to waste time. But it's the first 3 parts of bits you can do kind of intuitively just as you're reading the paper, once you get used to it.
Okay, perfect. I think, yeah, what I'd say is actually a lot of what we did. I know you said the first 3 parts, but I think once you practice this a lot and get good at it, you could do most of this before you decide to choose a question. Quite quickly, in fact. Reflective reflex. Chris, are you back?
Yeah.
I've got too many things on my screen. Yeah. All right. Perfect. So in reflective reflex, what did you actually learn from that question? Like, or what was the point of that question? Can you put that into words? Can you actually articulate it? Because if you can say what the question was asking, it shows you've really learned what you're meant to be doing. What about the question made this method work? In other words, would this method always work, or was it something specific in this question that meant that I could use this method in this question? What were the techniques I learned here that I could actually use in another question? And what we're going to be doing in this next section is showing you how we can apply the techniques we learned in this question to some other questions, basically. And then lastly, if you were to invent, so that was a 2-part question. If you were to invent a part 3, what would it be? And then actually, maybe you want to actually go and solve it and see, does the same technique work for the question that you made up? Which is really, really interesting, because if you can make up parts of the question, you're really getting inside the examiner's head and you're really figuring out how they create this question, and you'll be a lot better at answering questions in the future. So Chris, talk us through your reflective reflex for this question.
Okay, well, the first question is, what was the outcome of doing this question? What did we learn?
So are you trying to say, what did we learn, or what were we trying to do? Is that what's your actual question?
Yeah, so if you imagine part 1, someone's actually talking to you, they're saying, simplify this expression, show f of x equals this, and show this. What is that person trying to get you to do? Like, what does that person want you to do?
What's the final outcome of part 1, right? Is that what you're asking?
Yeah.
Okay, so what did the examiner want us to figure out in part 1? Put it in the chat to us. If you had to just say it in like one phrase, what were they trying to get us to do? Have a think and put it in the chat to us. Not very chatty, this bunch. I remember last time we did this webinar, we had loads of people replying. Just have a guess if you're not sure. Okay, so somebody says, okay, we were supposed to try and understand how to do part 2. We were trying to simplify the function quadratic. We were trying to, the aim, so remember, okay, I think if we phrase it like this, what was the aim of part 1? So the aim was, somebody says, to sum and cancel terms, to get a simplified version of the infinite summation, to trying to introduce you to how to approach a second part, knowing how to cancel terms in infinite series to a finite number. Interesting. Recognize that a fraction of the form a over 1 minus r can represent a geometric series, even if it's not meant to directly be one. Okay, so remember the aim of the whole part 1. I don't think I've ever seen an answer here that I think is the whole aim so far. Somebody says simplifying the function to create an easier sequence to understand. Interesting. Trying to make g of x as a sum of geometric series. To solve the recurrence relation. Ah, interesting. To solve the recurrence relation. to see that f of x can be expressed without infinities in a way that relates to a recurrence relation of an, express the coefficients in terms of n, which is interesting as well, how to write a series in terms of just two fractions with no unknowns, how to express a series, how to express the series, or do we mean the sequence? How to express a series as in terms of the nth term, etc., etc., etc. I'm going to just move down here, simplifying the function f of x into a non-recurrence relation. All right, Chris. So we've got, by the way, I don't think any of those things were wrong. Like the question did ask you to do all of those things, but what was the point, Chris? Tell us. What was the aim?
Okay, so well, I think the natural place to look for the aim is the last line. The last thing us to do is to find an is 2 to the n plus 5 to the n. So in this, that's half of the point, but we just need to reflect on what our starting point was, because what you've done depends on where you started and where you got to from there, and that determines the task you've just completed. And our starting point was, okay, we have this definition of f of x. It look like f of x is the central object in this question, but that's kind of deceptive because it's just defined in terms of a bunch of coefficients that we know nothing else about. So that definition on its own is kind of empty. Our real starting point is the recurrence relationship for an. That's the first time we're giving anything really concrete. And remember, our last line is also about an. So what we started with was a recurrence relationship. And what we ended with was an explicit expression for an in terms of n. So we've basically solved the recurrence relationship. And when you think about this, then the striking thing about it is that if you were just given a recurrence relationship, it's kind of unlikely you'd come up with this idea of thinking about a function f of x whose coefficients are the terms in the sequence. That's not a natural thing to think about first. But what the examiner is doing is showing, and this is a method people actually use for solving recurrence relationships, and the examiner is showing you this method, which is not easy to come up with on your own. So they're basically teaching you a method for solving recurrence relationships. And so the f of x here is just a tool. What we ultimately work out is the expression for an.
Yeah, I think it's quite counterintuitive, right? Because it looks like the f of x is coming first, but the f of x is defined in terms of these a's, and the a's are defined here by this recurrence relationship. So in the end, what did we end up doing? We actually ended up finding the nth term of this expression. So yeah, that's quite interesting. So as you said, the f of x was introduced simply to help us solve this. And you might not have thought it was the other way around. So that's interesting. Yeah. Shall we move on to the next point?
Yes. So our conclusion is that we were studying a sequence an, which is given by a recurrence relationship, and we did that via a function, which is the sum of an x to the n. So okay, that's kind of what we learned from the question. And bear in mind, this is the kind of thinking you're doing not while you're in the exam. That's not necessarily going to help you that much. This is the kind of thinking you do. So after you've done a mock, maybe, then it's a good time to reflect on the question and just play around with the ideas a little bit more, because hopefully they're interesting. Hopefully you can think of some more interesting things you might try to do with this technique that we've just learned. So, well, what might we try to do? We've just solved one recurrence relationship. Maybe we could think about other sequences. So we basically found the nth term of a sequence. What other sequences could we look at? And connected with that question is the next point. Now, how could we alter the recurrence relationship? Because the recurrence relation kind of defines the sequence. Well, that and the first couple of terms. So now we're kind of thinking about how you could make a part 3. Bear in mind, we've got a part 2 here where so people who said that part 1 is teaching you how to do part 2 aren't wrong, but it's kind of teaching more than that. It's teaching you a technique that can apply to lots of sequences. Part 2 actually is quite similar to part 1 though in how it goes. If you actually attempt the question yourself, you'll see this. We could make it more different. So I don't know, Pal, do you want to ask in the chat, like what experiments?
Yeah, sure. Okay, so is your question, we've got a nice suggestion in the chat actually. One person has said, if you do this with Fibonacci, the Fibonacci sequence, do you end up with a golden ratio?
Yeah, you do. But even if you didn't know what the golden ratio was, you could think, well, what's another sequence I know a bit about that's defined by a recurrence relationship? The Fibonacci numbers are defined by a recurrence relationship. It's an is, if you think about the coefficients, it's an is 1 times an minus 1 plus 1 times an minus 2. So if we just run this question again, but with that sequence, what do we get? And you can get an explicit expression for the Fibonacci numbers. It's a little bit more complicated, but that's something that's worth trying yourself.
She said that's so cool in capital letters. That's awesome. It is pretty cool. It's really cool. Somebody says possibly you could express an in terms of more than just 2 previous terms. Yeah, that's kind of a good way to think about this. And this is something the examiners are almost doing when they come up with parts 2 and 3 themselves. It's like, okay, we've done part 1. How can I break part 1 or make part 1 more difficult? And one way is let's just add more terms. Let's have an minus 1, an minus 2, and an minus 3. So yeah, you could think about how you would solve it if it had 3 terms or more terms than that. Somebody says if x and f of x are just tools, wouldn't we just be able to use a specific value of x that might make the problem easier? In some circumstances, maybe yes, but here not so much, because if you just substitute in a value for x, for instance, you don't have a quadratic you can factorize when you do the simplification step. But it's an interesting thought. Another problem is you have to make sure you choose a value where the series actually is defined. That's an interesting thought, yeah, but it is much easier when the x is there. So somebody says, why is this after problem planning? How do we know where to reflect before beginning the question? Huh? This is afterwards. I don't understand the question. Anyway, so somebody says, sorry, if you found the recurrence relation of the first one, can you see this one, Chris, the question? If you found the recurrence relation of an, oh, not an, it says an first. How can you find the recurrence relation of a P.R.O.F sequence? I don't know what that is. Do you know what that is? If you found the recurrence relation of an first. I think if we don't understand the question, we have to leave it. Yeah. No. So you can't solve the recurrence relationship in a different way and then extract f of x because it says hence. It doesn't say hence or otherwise, it says hence. So they're kind of bullying you here and saying you have to do it our way, even if you know another way to do it. But and not all questions are like that. Some questions, I mean, in fairness, actually, they do often say if you get to the right answer by a valid method, you get all the marks. They don't normally word it this strictly, so they don't normally leave you. Normally they say hence or otherwise. Yeah. That's a very normal expression. Yeah. Okay, cool. Let's move on. So what's next, Chris? So I think maybe we weren't clear what reflective reflex is because a couple of people have asked this. This is we're imagining now we've done the question. Oh yeah. We're not going to do the question here in this presentation because that's not like methodology. That's just working out. So problem planning is what you do before you do the question. Reflective reflex is what you do after you finish the question and maybe looked at the solutions in your own time, so you can extract more from the question. I do want to mention one more thing here, like how can you, I said, how can you break what happened in the actual question? And we said, well, you can make it more difficult by adding more terms. Another thing here is, when we wrote f of x as this 1 over 1 minus 2x plus 1 over 1 minus 5x,
that's basically doing partial fractions, and that worked because the quadratic factorized into 1 minus 2x and 1 minus 5x. So you might want to think about what if it wasn't that convenient and it didn't factorize. And that is also an interesting question. But yeah, so if we go on to the next slide, one thing we advise our students to do is make a cheat sheet, kind of summing up what you've learned from the question and reflecting on the question. Okay, to answer the chat, well, I meant factorize over the real numbers. So this is just an example. This is maybe more detailed and generalized than you would actually be able to do in your own time. But we're kind of showing what you want to do is take note of the very specific things you've learned so you can watch out for them in future. And that might mean like seeing the exact same thing cropping up in future. It might mean seeing something similar, but because you reflected on this, you can kind of then generalize this or adapt it to something that's similar but not exactly the same. So if we summarize our specific technique here, what did we learn? Well, the first thing we saw was if you have a recurrence relationship, our previous one was basically an minus 7an minus 1 plus 10an minus 2 equals 0. So we rearranged it to get 0. And that corresponded to our quadratic x squared minus 7x plus, which we understood. Yeah, sorry, 1 minus 7x plus 10x squared. I think I might have written this the wrong way around, but it doesn't matter. Sorry, I think the 0 and the r in the subscript should be swapped a bit.
I think it doesn't really matter for this point.
Yeah.
The point is, we learned that if you had a specific recurrence relationship, then f of x times a very similar looking expression would simplify nicely.
Yeah.
Right. That would be something, again, remember, we would be making this note after we'd done the question, but we knew exactly what it was. We're still kind of guessing if we haven't seen the whole thing. But this is the kind of thing after doing the question that you would want to write down. Yeah.
I should say, maybe you wouldn't generalize it like this. Maybe you just say, like, keep it as a quadratic if you didn't think about how to generalize it. Just showing you can be more general. So when you note down a specific technique, you want to remind yourself where it came from. So the question in the paper, and maybe a summary to remind yourself what the question was about. And you also quickly want to think about, okay, when does this work and when does it not work? So what conditions were there for it to actually be useful or to be possible? So this worked when we were given the recurrence relationship, but we didn't already have a nice expression for f of x. So if we didn't have the recurrence relationship, or if we already had the expression for f of x as the sum of two fractions, then we wouldn't be able to do this, or we wouldn't need to. So, but that's kind of what the second column says. If we don't know the recurrence relationship, or we can do something simpler, then we won't use this. Quickly talking through the second row, one thing we saw was when you try and find f of x, you're really doing some function divided by another function, then you have to simplify that into the 1 over 1 minus 2x and 1 over 1 minus 5x. And we said that's nice because terms, I've just generalized this again. So we said, oh, 1 over 1 minus 2x, that's actually a geometric series, or an expression for the sum to infinity of a geometric series. And so anything that's like a constant over, well, as it says here, a over b plus cx, something like that, you can always write as a sum to infinity of a geometric series. Okay, except for unless you choose b and c are both 0 or something like that. But okay, imagine it's sensible. So again, we know what question that comes from, and we know what needs to happen for this to work. So we need to be able to factorize it basically, so all the denominators are of the form like a constant plus a constant times x, and it looks like this only works when all the numerators are constants. So for instance, we had a 1 on the top of our fraction, 1 over 1 minus 2x. You can actually think, okay, if I put a power of x there as well, maybe it would still work, but that's generalizing a little bit again. And when would this not work? Well, if the bottom of our fraction q of x didn't factorize, then we wouldn't be able to make all these fractions in exactly this form. So that's something to watch out for. And like when you're making notes, you might say, as I mentioned before, okay, well, what would happen to the question if it didn't factorize? So you can maybe make a note to yourself in your cheat sheet and then do some more practice in your own time, check what happens in the case where the denominator doesn't factorize. Or if it has repeated factors, which is another thing that can go on. But that's the kind of thing that you come up with just by thinking about the question more in your own time.
So yeah, so far what we've looked at then is problem planning. So how to think about the question before you do it. This is part one of reflective reflex. So it's thinking about what techniques I used here and where I could apply them elsewhere. And then I guess the second part is actually when you do another question, thinking back to when you did this question and trying to apply those techniques. So what we're going to look at now is a couple of questions which are on a related topic. And imagine this was in a few weeks' time after we've done this question. And let's think back to our cheat sheet and be like, how can I reuse those same techniques in a later question? So tell us, Chris.
Okay, so we might have to give you a minute to read this, but I'll read it in a second just very quickly as well. But just think about how the step one question we did before might be relevant to this. And then how is this different or harder? So if I read this quickly, it says we've got the coefficients in the series S, which is a third times x plus a sixth times x squared plus a 12th times x cubed, etc. And the rth term is just arx to the r. They satisfy a recurrence relationship of the form a r plus 1 plus p times ar is 0. So we're meant to assume p is a constant. It says write down the value of p. By considering 1 plus px all times s, we're asked to find an expression for the sum to infinity of s, assuming it exists, and also an expression for the sum of the first n plus 1 terms of s. And in part 2, it looks very similar. Now we've got a series T, coefficients are 2 plus 8x, it's 18x squared, 37x cubed, etc. They satisfy a reconstruction of the form a r plus 2 plus p times ar plus 1 plus q times ar equals 0. We're asked to find the sum to infinity of t again, and then it says by expressing t in partial fractions or otherwise. So here you see that or otherwise we mentioned before. Find an expression for the sum of the first n plus 1 terms. So our question was, how is this related to the question we did before? How did what you learned from that, how could what you learned from that help you in this question?
Okay, so how could what we learned, we should say, in the previous question help you with this particular question? If you want to put it in the chat now, somebody is saying, thinking about recurrence relations as coefficients of a geometric series. Yeah, great. Anything else? Any other things that we saw before that could help us? Oh, that looks similar between that question and this question, even. What else looks similar to you? Express S in the same form as f of x from the previous question. So you could express S in that same form, but actually they've kind of given you a hint here. They've given you another type of thing, another type of expression to look at or simplify. Somebody says transforming 1 plus p times x times s equals t. Where are we getting the t from? Equals something, whatever it is, whatever the answer is. And then they're saying maybe if we divide by this, we'd get some kind of partial fraction. They're saying maybe t and s are Taylor series based on a different function. Find the expression of the coefficients. 1 plus px times s seems a lot like how you derive the summation for a geometric. Interesting. What would happen in this case then? Somebody says it's a recurrence relation defined by 2 terms, but there were 3 before. Before we had a quadratic, now we have a linear. Ah, interesting. The a terms are also geometric series. The first 3 terms look like a geometric. So here we're saying this expression itself seems to look like a geometric series. Interesting. And then for part 2, you could use a quadratic substitution instead. So here they gave a linear substitution. We've seen a really similar one on our cheat sheet, if I'm not mistaken. And then there's going to be a very similar thing that we can do here, but yes, instead we're probably going to use a quadratic. Chris, right? What did you think about in this question?
So yeah, I actually think it's more important to think about part 2 here. So part 1, some of you did identify, is actually just a geometric series. And the reconciliation actually tells you that, because if you rearrange the reconciliation, it just says AR plus 1 is minus P times AR, and that's the definition of a geometric series. So it's telling you to do it in a particular way, which is multiply by 1 plus px, simplify, but you're expecting it to be geometric. So that bit's not actually that difficult. It's part 2 where, having done the previous question, helps you see what to do more easily. Because we saw in the previous question that it was useful to multiply by a quadratic. That's something you might not immediately think of if you've never done that kind of thing before when you came to part 2, but it is what you need to do. Instead of multiplying by a linear term, you want to multiply by a quadratic. You're also going to need the coefficients of that quadratic. Instead, they're just giving you constants p and q, but we didn't write this in our cheat sheet, so as not to spend loads of pages in our cheat sheet, but we did also see that trick. Oh yeah, if you've got unknowns in your recurrence relationship, you can find them by substituting in some of the first few terms. Probably something you've seen before anyway, but it's useful to make a note of. And yeah, we've got enough terms here to do that, so we can find p and q. And then we can construct a quadratic, multiply t by the quadratic, do something similar to what we did in the step 1 question just before. And we are expecting it to look similar to our expression for f of x from the previous question, once we rearrange. The final question you might ask yourself is, well, okay, this is similar to that step 1 question in a couple of ways. How is it more difficult? Because this is step 3. It's not the hardest step 3 question in history, but it is, if you hadn't seen the other question, it would be tougher than the step 1 question. So what makes it harder? And there's maybe 2 important things.
Okay, so put in the chat, what do you think makes this question harder than the one we looked at before? Somebody says less scaffolding. So maybe by scaffolding, it's like, yeah, there's less hints. The connection of part 1 to part 2 is more, the connection of part 1 to part 2 is more obscure, less words, much less information is given to you in the question. The last question gave you the process in part 1, but this one doesn't. It's more abstract. There's no values for us to sub in, for example. There's more red herrings. Having to find the sum of n+1 terms instead of a relationship, or just to look for, yeah, instead of just solving for an. You have leftover terms at the end when you compute x squared plus px plus 1 times t. You have more leftover terms.
Yeah, I think the chat's kind of identified the 2 key things. Firstly, the step 1 question took you through step by step. It said simplify this, hence show this, hence show this. This gives you less guidance, especially in part 2. Secondly, we've got an extra task, which is to find the sum of the first n+1 terms, which means you're kind of looking at a different series then, because S and T are sums to infinity. So you've got to write down the sum of the first n+1 terms and do a similar trick with it, and maybe be a little bit more careful, because as someone said, you might have terms left over at the end in some sense.
Okay. I think I'd like to make the point that, so this is a step 3 question, which probably if we'd seen on our own, we might have found it a little bit harder. But the fact that we did the step 1 question before, and importantly, because we reflected on it and took our learnings, it actually made this step 3 question easier. So there is a lot of power in actually thinking about what you've learned and where and when it doesn't apply, so that when you do come across something similar in the future, like, you have all these tools in your tool belt, you know, that you can just use. So making that cheat sheet is a really, really, really important thing. Shall we move on, Chris, to the next slide?
Yeah. I'll just, okay, I'll read this very quickly and you can think about the same thing. this one's maybe not quite as similar, but there's some connection. So now we're told that a and b, the coefficient of x to the n in the series expansion of this fraction, 1 plus x over 1 minus x all squared times 1 plus x squared, where mod x is less than 1. We're asked to show using partial fractions that an is always equal to n plus 1 or n plus 2, depending on the value of n. And then we're asked to use that to approximate 11,000 divided by 8,181. This is the whole of the question, by the way. It's a bit shorter than the others. So what did we learn before that's relevant to this one? Here's maybe one key thing that I'm looking for.
So Isaac, feel free to like unmute and say stuff. You don't have to put it in the chat if you want to say about the previous question. Cool. Similarly for Adam, if you want to add anything, feel free. Okay, so everyone have a think, put in the chat, how do you think the step 1 question was relevant to this question? Okay, I'm going to read some of these out. So either use a Taylor series to find an, or use a geometric series of each partial fraction to find an. Expressing rational functions as infinite series. The question also gives us certain parameters or restraints, like mod x is less than 1, maybe, is what you mean. Algebraic fractions, similar parameters for x. You can express it as a sum of multiple fractions as well. So yeah, basically using partial fractions on this could work. Binomial, somebody says, why isn't this fraction simplified? Okay, I don't know, I think
you might be reading it as 1 minus x squared rather than 1 minus x all squared, if you're expecting it to simplify. In fairness, that's also how I read it the first time, because my screen was too small.
Somebody says splitting into fractions and finding series by using the same technique of 1 over 1 minus x, infinite sum of geometric series, etc.
Yeah, I mean, that's the main thing I'm looking for. So it says to do partial fractions. So you do want to do that instead of binomial expansions, which I think someone mentioned, which will get very messy. But then how do you convert partial fractions to finding out about the coefficients? Well, we've seen the method already. If you have basically anything over something like a plus bx on the bottom. So here on the bottom, we're going to have things like 1 minus x or 1 plus x squared. Terms like that, you can just convert to geometric series. And that lets you read off some coefficients. That's not going to be the whole story because first we have got this 1 plus x squared there, which you're circling around. That's actually not so bad because well, I'll leave you to think about this question in your own time if you want to. It's from step 2, 2008. You can deal with that in a similar way to what we were doing before. The bigger deal is actually the repeated factor on the bottom. But I think if you start thinking about it in a similar way to the previous question, you can figure out how to deal with that as well.
All right.
And that's all I wanted to say about this one.
Okay, perfect. So let's move on then. So we've looked at P and R in P.R.O.F. And we've got O for outline and organize. So in step, it's actually really important to lay your work out properly. I'd like to kind of rush through this a little bit so we have a bit of time for question and answers. So how do I lay out my work? How do I make it clear? Using diagrams, making sure the logic I use is valid, and making sure that I don't miss any steps and I've got a fully complete solution. So what we're going to show you is some of our past students' work and maybe where they didn't lay their work out properly. Chris.
Yeah, so just very quickly on these, this person is dealing with complex numbers. If you haven't seen those yet in year 12, it doesn't really matter. What I've done is rewritten each one in terms of some new variables st, x, and y, but they haven't defined those yet. And you can probably infer by context what each one is meant to correspond to, but it's not good practice. I should really write, okay, w is equal to this s plus t times I, z is equal to this x plus y times I. Probably also worth writing down that st, x, and y are all intended to be real numbers, because that matters later in the proof. So you can read it off by context, but it's going to be easy to forget unless you write it down. This one, here they're trying to show, this is notation for showing one sequence, like all the elements of a sequence are less than elements of another sequence. And they're basically dividing into cases, the cases where n is less than 1,000, equal to 1,000, greater than 1,000. But because I think actually when I was marking this, I wrote on the case headings to kind of break it up, because if you don't do that, again, you can work it out by context, but you have to take 5 seconds to parse what's going on if you've just got 6 seemingly unconnected lines. So adding headings is useful for making your work readable. And it also helps you show you've got all the cases, like they're exhaustive cases.
Okay.
A common issue with students' work is like notation for limits. So we're talking about what happens as x goes to infinity. It's best not to write x equals infinity because it's not really sensible. And you can get lots of expressions like infinity divided by infinity, infinity to the power of minus infinity. Like, how do you evaluate those? So it's much better to talk using proper limit notation, which if you haven't seen much of in year 12, you will later on.
Well, you say you will. I don't know if there's that much on it in A level, but it's definitely the kind of thing you need to get good at for STEP.
Yeah, it is something we sort of cover in our courses because it is important. This one, basically this person needed more sort of logical annotation of the connections between steps. So here the question actually asked you to show that line 2, which is that either n is greater than 1,000 or less than 0, that implies line 1.
Oh, okay.
But they started with line 1 and worked towards line 2. And that is something you sometimes see at school. It is okay as long as all your operations are reversible. But if they're not, then the logic breaks down. So we use these double arrows to indicate that we're only doing reversible operations, and that makes our argument watertight. But otherwise, it would just be invalid.
Okay.
Okay, here we've got a kind of geometric argument. You can see if the green writing wasn't there, this would be quite hard to interpret, right? It's very hard to see what's going on just by looking at the students' work, because they're just writing down all these quantities, but you could just about interpret them from the diagram. But I remember it took me like 5 minutes to put together what they were trying to do. So if you're drawing triangles and talking about, here they're talking about similar triangles, but they haven't said that. So firstly, if you're doing an argument by similar triangles, you can just write similar triangles at the top to say what you're doing. And then you need to very carefully identify which triangles in your diagram you're using, especially because often lengths repeat. Like in this diagram, you've got 2 squares. Some side lengths are going to be the same in different triangles. So you need to identify carefully which triangles you're talking about. So you can see on the right-hand side, I said, okay, identify, maybe label the corners of your triangles. Say these 2 triangles are isosceles, these 2 sides are equal, these 2 angles are equal, therefore the triangles are similar, therefore this ratio of sides equals this ratio of sides. And that would be much clearer what the argument actually is.
I think that the word argument is quite important. You're not just like working it out, you're actually trying to show something. You're trying to show your reasoning and your justification for why that's the case. So writing it out with words is not a bad thing at all.
Yeah. In particular, the student didn't show their 2 triangles were similar. They recognized they were from the picture, but if you don't explain why, then you might lose marks. Yeah.
Cool. And then lastly, fast assessment. If you do problem planning, reflective reflex, and if you lay your work out nicely, you will get fast. You will get much quicker. So we said that the problem planning, we spent probably 15-20 minutes on it here, but in a when we were doing a step paper, we might be able to do that in 5 minutes. And this is just comes with practice, practicing lots and lots and lots and lots and lots of questions. So yeah, getting fast and fluent is a natural consequence of the P.R.O. of P.R.O.F. So how do you get in these questions? So if you're going to roughly try to do 4 questions, that's about 45 minutes per question, and you want to give yourself a few minutes to read at the beginning and pick the questions. If you do 5, it's about 36 minutes. If it's 6, then it's 30 minutes to question. But bear in mind that sometimes question 1 and maybe sometimes question 2 can be shorter and quicker questions. So you could spend less time on them and a bit more time on the other questions. In terms of choosing questions, do at least, I would say, you don't have to read them all thoroughly, but do at least glance over all of the questions. Don't just say, I'm going to start with number 1. Like, glance over questions at the beginning, try to problem plan the ones that you think, okay, I can make progress with, and do those questions first. And as Chris has written there, annotate the questions. So like, where we saw mod x is less than a fifth, like annotate that kind of thing. Annotate core instructions so you don't forget about them, because it can be very, very easy to forget. And say you're doing a question and you're stuck on it, when should you move on? Give yourself at least a few minutes to think about the question before moving on. But at the same time, I suppose if you're really stuck, don't spend too long on it, because otherwise you might miss out on doing another question. And I think that's just, this kind of thing comes with practice. And so it is really, really, really important to do lots of mocks or step papers in time conditions.
It might be worth saying that if you're in year 13, a lot of you might have done, say, the MAT for other universities. And so your exam experience will be different from what was needed for the step. Because in the step, you're expected to get stuck and have to think for some stretch of time in the question, and for at least some questions, which you maybe don't have time to do in an exam like the MAT.
Okay. And then how much work is going to be required of you between now, say, and when you actually come to do this test? So for people who are on our program, somebody put in the chat, what is the mastermind program? So essentially, here at the Oxbridge Formula, we kind of train students to start thinking about problems in the right way. We have a 1-year program for year 12 students, which starts now, ends in December, and a 6-month program for year 13 students, which starts now and ends when the step papers start, basically. And it kind of, I'm going to talk about it a little bit more in future slides, but during term time, we expect our year 12 students to put in a minimum of 5 hours of additional work per week. So we will give you the problems, we'll give you the questions, we'll give you the resources that you need, but obviously the work has to come from you. So that's kind of how much we would expect. For our year 13 students who are currently now in year 13 and have got their step offers, we're probably looking at around 7 to 8 hours of work per week, which kind of includes 2 past papers. Especially if you're doing step 2 and step 3, you want to be doing quite a few papers a week. And then reflecting on the questions you did and making sure you do additional questions during the week, because if there's, say, 12 questions in a paper and you only did 5 or 6 during your mock, you've still got 5 or 6 questions that you can do during the week, and reflect on the questions that you did as well. So that's kind of the level of work that we're asking for. Now, let's make sure we do that properly. What kind of mistakes do people typically make? Number 1, they're not doing realistic or effective practice. So they're not doing any papers in time conditions. Now, probably this is going to be the first paper ever that you're going to have done, which is 3 hours long. You might have done another one, depends. But, you won't have seen many 3-hour papers at this point. Plus, you probably haven't seen anything as challenging as a step. So doing them timed is absolutely important to figure out how long you need to spend to pick your questions, to figure out how long you need before you move on, to see if you need time to check, etc. Another mistake people make is just diving in head first. Hopefully, if you take one thing away from today, do not dive head first into problems. They might just start writing too quickly. I think that's kind of a similar point. Like, as soon as you think, oh, I know how to do part 1, let me start writing. No, but then you might miss the links between the parts of the questions. So don't do that. Not planning or reflecting, and cramming. I just don't think it's possible to cram for step. Like, it's not possible, full stop. So you need to start now, especially if you're in year 13. And even if you're in year 12, our programs for year 12 have already started, and we're already starting to develop our students' problem-solving skills. So look, if these are mistakes you're making, what are the solutions? Start early. Oh yeah, it says it there. Start now. I mean, whatever year you're in, there is no better time to start than the present moment. Do not, I speak to a lot of students regularly who say, oh, I've just flicked through the papers and I did a few here and there. Like, make sure that you set some papers aside for mocks, because you need to experience that. I don't even think some, I think at least 5 or 6 years of papers you should be doing in time conditions. And then you can take extra time afterwards. Nobody's saying you only have to spend 3 hours, but give yourself 3 hours and see what you would have got, and then spend extra time finishing the questions before you mark them. So do mocks in realistic conditions. Take time to plan each question and take time to reflect afterwards. Okay, hopefully you've got that from this presentation. And maintain a cheat sheet. So after you do your reflection, fine, it's all great to have it in your head, but you want to be able to look at it later on. So write stuff down. Struggling for success. What mistakes do people make? They don't do any work outside of mocks, they just do mocks, and they don't bother to do corrections after mocks. So like once they do a mock, they like mark it and they're like, that was my mark. They don't bother to reflect on it afterwards. They don't bother to try and spend extra time on questions that they didn't quite finish. I think that's a mistake we're saying here. Only attempting questions once and never like going back and looking at questions they've done before. Looking at solutions too quickly. So if you do the mock and you're like, okay, let me just do the solution, mark it, boom, that's done, that's my step preparation over. That's a huge mistake. Not realizing the importance of independent study and struggling. So after you do your mock, take some time out and come back to that same question before you mark it, because you need to give yourself as much time as possible in letting your brain come up with a solution before you look at the answers. And then finally, underestimating the difficulty of step and not putting enough time or work in. So what are solutions to this? Come back to questions after you did a time mock and spend time solving them before you mark it. Don't just read or watch your solutions too soon. Do look away from solutions when you get a hint. So say sometimes you, after the mock, you look at the solutions, get a little hint and then carry it on your own. Do not just keep relying on the solutions. And then how do you maintain your progress? What do people do? Oh my gosh, the number of times people tell me they don't mark their work. What is the point of doing the practice if you're not going to mark it? You don't even know if you got it right. You don't even know there's a better technique. It's crazy. However, there is times where you might not be able to mark it properly, because in some of the older past papers, there are no mark schemes and you might not know how to mark it properly. So in that point, ask one of your tutors to mark it. If you're working on a program like ours and you're getting one-to-one tuition, get your tutor to mark it. Isaac and Adam, I'm sure, are used to marking step questions for their students. It's really bad to just see your strengths and not identify your weaknesses. Like, what are topics I struggle with, or what are techniques I find difficult, etc. Like, identify. Not learning from experience. So if you got something wrong, not kind of reflecting on why you got it wrong. Not realizing that later papers have got harder. So if you're just practicing, like, I don't know, 1999 to 2005, they're not going to be as hard as the kind of questions you're getting now. So don't lull yourself into false sense of security thinking, yes, and I got all the 1999 paper right. It's not reflective of what you would get now. It's so important to do recent mocks. Solutions. You must mark your work or ask somebody to mark it for you, because there aren't any mark schemes for older papers. Review challenging questions and topics with a tutor. Make notes on what you did well or badly in papers, and make a mental note of how the papers have changed. Review your notes and cheat sheets regularly to revisit what you've learned, because you probably had, is it called the forgetting curve or spaced repetition? So if you do a question, just thinking about what you've learned like 3 or 4 weeks ago is useful to kind of keep it in your brain. So if you are doing STEP this year, do as many STEP questions as you can. Do time mocks in real exam conditions and reflect on previous questions. So if somebody, like, we had a student, Oscar, who got SSS in his exams, like extremely well throughout his degree. I think he got like 95% in his like finals in Cambridge. Last year he told us, solve every question in 2 ways. So here they told you, hence do it this way, but now find another way to do the same question. And that improves your understanding of maths in such a big way. So that'd be great. Now, Chris, can you talk us through this timetable, please, for how one might want to structure their week if they're in year 13?
Yeah, and this is just an example. Obviously, it depends on when you actually have spare time. We're going to put the weekend at the beginning, because that's when you have the time to do mocks that you might then continue to work on for the rest of the week. So Saturday mornings, we have, at the moment, that's when we have our P.R.O.F workshops. Then after that, maybe you have time to do a step 2 mock. So we said maybe this is what you're doing in March. So not immediately before the exams, when you might be doing like recent step 3 mocks. But, okay, now you're doing a step 2 mock. And in the evening, so Saturday and Sunday, you're doing that mock in the afternoon. And then in the evening, you can continue to work on some of the questions you didn't finish in the time, because if you only do the timed mock, you're only giving yourself 3 hours to think about the questions, but more time thinking about them means more benefit. So maybe later you come back to some, maybe you had some ideas over dinner, you can just work on them a little bit afterwards. I think the second one should say 2015, actually.
Okay. Yeah.
It doesn't matter one way or the other. Then maybe later you have a free period, you can continue with questions you didn't finish or you realize later you made mistakes on in the paper. And then once you've got as much as you can out of like struggling with the questions, then you can go to the mark scheme and mark your work. And see, firstly, how much you would have got right just based on what you did in the time conditions, but also whether when you were doing the unfinished questions afterwards, you got the right idea, and look for if there are alternative methods and so on. And it says RR here, so that's your reflective reflex. So after you've seen the mark scheme, reflect on what you've learned from the questions and make your cheat sheet. As we saw earlier, like reflective reflex can go into quite some depth, so that might continue afterwards, even if you have the time. But at least you can do the initial reflection there. Wednesday evening, maybe this person has tuition. Some tutors might set work for you, in which case that might be done on a previous evening, for instance. And then likewise for 2015, you can continue working on your unfinished questions and then do the marking and reflective reflex later on.
Okay.
It's also worth saying it's always worth like not spending a whole day just doing one paper, spreading it out over time, because sometimes ideas come to you when you've had a night's rest or a day in between, some time away from the paper.
If you are currently a Year 12 student, just do as much problem solving as possible. That's UKMT, MAT questions, and so on and so forth. I'm not going to go through this whole timetable because I really want time for the Q&As, but you would have a similar thing. So you might come to a maths workshop on the Saturday, you might attempt a mock on the weekend, finish on unfinished questions and reflect. So now it brings us to the Q&A, and I'm going to get the Q&A questions out. We don't have that many actually this time. So is there going to be a recording of the webinar? Yes, there will be. We'll send it out over the next few days. If you have time in a step question, could you answer more than 6 questions, Isaac?
I wouldn't, because unless you have like significant time, which is unlikely, like each question takes half an hour probably. So to do 7 questions, you'd really want to have done like half an hour after you finish your 6th question. It's a lot wiser to look back over the questions because there is like a max mark. You can only get 120. There's no benefit unless you thought one of your questions is really bad, but it might still be better just to work on that. Like I wouldn't advise trying to do more, and often like a lot of the candidates do more in step exams. That's like something they always comment on in the exam reports, but those students who do more are often weaker because what they've done is just jump around questions. So they may have attempted 8, but if they've done, I don't know, if 6 of those 8 are like very partial, then it's not actually giving you a strong score overall. And I think it's important to remember Cambridge, like when they make the decision of who actually gets in, they'll look at your script. So like if you get a 1-1, you get in, but if you miss the boundary, they'll look at your script, and if they see you've got a 2-1, so that's a 2 in say step 2 and a 1 in step 3, and you've got that by doing lots of partial questions, they may be less keen on you. Or if they see you're someone that's attempted questions solidly, so you've done like 3 solid questions, then they might like you more. So I would not do.
And also you've got to remember that the second half of questions is harder. So 2 things. Number 1, they will only mark or count your best 6 questions. So okay, if you do 8 and you just do like 1 mark on each of 2 of the questions, then fair enough, and you couldn't get any further, then they'll look at the rest of the questions. But if you do 7 questions really well, they're not going to all count. So you might as well do them extremely well and just do 6, I would say. A lot of the marks actually are towards the end of the paper. So for example, in that question we saw, my estimate would be there might be 8 marks for the first part and 12 for the second part, because the first one had more hints and they give you a lot more scaffolding. And the second one, you had to do a lot more thinking. Okay, how can I apply what I learned there? But they haven't told me what the form of the expression is that I should be looking at, etc. So often there are more marks for later parts of questions. Chris, did you want to add anything?
I was just going to say basically the same thing. So no,
Okay, cool.
nothing to add.
All right, perfect. So question for you, Adam. If you don't do statistics in further maths, is looking at the statistics part of the paper a bad idea? I don't know do you feel comfortable answering that question?
Yeah, so I didn't do further maths. Actually, I'm not even from the UK, so I self-taught everything. And so I would definitely say, especially if we're at this stage now, it's well worth looking at least some of the content in the probability and statistics questions, particularly the more counting combinatorics and just pure probability ones, because they're actually some of the most straightforward step questions are in those sections. And you're giving yourself an extra few questions that could mean the difference between you having an extra bit to solve just for the sake of knowing what is realistically quite a small amount of content. So I think if it's a month before the exam and you haven't looked, then I would leave it. But when it's only January, it's well worth looking.
Okay, perfect. And I actually agree with that. Some of the probability questions are quite nice sometimes. I think also some mechanics, like you can pick a couple of topics, like mechanics is like projectile motion typically, I think is quite nice.
Yeah, and collisions, they're quite straightforward. So you can just, and they're topics you can do in isolation as well. You don't necessarily need to have done them in school. So you
might have done them in physics as well. You might have done them in physics and not in maths, but you could maybe still do them. Isaiah, did you want to add anything?
Yeah, I was also going to say, yeah, like just because you don't like a subject at school, like statistics often, especially in the UK system, is like can be very dull, because you do like chi-squared tests, hypothesis tests that are they're very just dull and formulaic. But the stats and STEP is normally a lot more fun. So I think just because you don't enjoy something in school, I wouldn't like rule it out.
Okay, perfect.
I just want to add one thing, which is for mechanics in particular, I think it's worth doing a fair bit of practice, just because you start to see is the questions are more repetitive than the pure maths. So it's easier to get really good at certain kinds of question, like as you were saying, collisions and projectile motion. That it's not like the questions are all the same, but they're all like they share 50% of their DNA. So once you get good at them, if you see one of those questions in a step paper, you're almost certainly going to be able to make a good attempt at it.
Okay, all right, next one. How often do you find similarities between multiple past paper questions? Isaac?
I'd say quite a lot, especially if you go back far enough. They're often kind of repeat questions, like not that often, but they do. Yeah, but I think the one thing is with past questions, like it's only really worth it if you remember them, because you can do loads of past questions, but if you forget everything, which I kind of do, I'll have seen a question and I'll be like, I can't remember how I've done it before. It's quite annoying. So it's worth like looking over questions when you've done them just to remember the techniques.
Yeah, I'd agree. They, particularly more recently, they like to take quite old questions and just make them slightly harder. But they aren't immune from taking a whole question from 11 years ago and just putting it straight in and just hoping not too many people have seen it before. So yeah, but like going through past questions, trying to memorize them to hoping they appear in the exam is not a strategy for success.
It's not about learning the questions off by heart. It's about understanding the underlying
exactly
question, right? Like, I think hopefully we've tried to get that point across today. Okay, right. Would you recommend doing work in rough first and then doing a neat write-up? Adam, what would you say?
So I'm one of those people who did some of my rough work off paper. I think it depends how neat your rough work is. Some people I know can just do everything straight away. And then I'm the type of person who, like, if I'm doing a calculation, I might just do it to the side, but like it'll still be on the page, just slightly separated from my answer. Absolutely do not solve a question and then try to write it up afterwards. It's a massive waste of time. But like, having a clear area for rough work at the side, if you're just, multiplying some numbers or something, is perfectly fine.
Yeah, I just wanted to say, I think this is where problem planning comes in, because sometimes you often some parts of the question, you know roughly what's going to happen. Like each step, maybe you have to think about like exactly what number goes here. Like does this work in both directions and so on. You know roughly what you're doing line by line. Other parts you can kind of see when you're planning it. There's going to be some algebra here. I don't know exactly what's going to happen. I'll need to do this rough, and then once I've worked out what's going on, then I can write it up.
Okay. Is it worth doing step 1 papers at this stage? They said they're in year 13 and they need to sit step 2 this year.
I'd say yes. Like I wouldn't linger too long on step 1 because it is easier. But if you're just starting step now, I'd definitely it's a lot easier to start with step 1 and build up some momentum and then hit step 2. But I'd only leave it like 3 or 4 weeks because you want to get on to step 2.
Yeah, I would agree as well. That if instead of just going straight from A level to step 2, you might as well use step 1 as a stepping stone.
Yeah.
No pun intended. Anyone else want to add anything to that?
Yeah, I would also say, and I know I've given advice to the people I know, if you're going to do some step 1 with the goal of moving on quite quickly, try stick to the later step 1 questions, because like you don't need to save them for mocks, and they are significantly harder and slightly more towards the style of the step 2 easier step 2 questions you'll be starting on. So yeah.
So would you say maybe what 2017 onwards, something like that?
Yeah, like 2016, 2017 is when they start getting noticeably harder. So
okay, perfect. That's a great tip actually. Does Cambridge look at the UMS of every A-level module? Sorry, A-level maths module, or just the final grade? And are retakes of A-level exams worth it if one module wasn't too good? Isaac?
I was under the impression UMS was scrapped, but I guess I might be wrong on that, because that was just
UMS isn't scrapped, but AS levels are scrapped.
Okay. Yes.
So what that means? Go on, Isaac.
I would doubt they would like look that intensely. Like they had like Cambridge, especially for doing maths, they were like overwhelmingly good at step. Like even if you got really messed up your maths A level, so you got a B in A level maths, I got 1 in step. I think that's quite a strong chance they would still let you in.
Yeah, I'm pretty sure. Like obviously, do not aim to not get your A-level grades. I mean, that's crazy. But I think what Isaac's saying is, if you are getting a 1-1 in step and you got a B in your A-level, something that went massively wrong in your A-level, like there's no way you could do really well in step but not be good at your A-levels. I don't know. So like basically, I think the point is ultimately in the end they mainly care about step and they don't care about like 1 or 2 marks here or there in your A-levels. In the past for Cambridge, they used to look at your AS. They used to look at your AS module marks in order to figure out how well you'd actually done, especially before. No, that was ages. I was going to say before the A-star was introduced, but that was literally ages ago. That was like my day. In which case they needed to know a lot more because they weren't even A-stars. Chris, go on.
Well, I want to look up the exact wording Cambridge used on this. So as you say, if you're doing like a linear A-level, like you tend to do in the UK, then obviously you won't have UMS for your first year because you won't have taken, you won't have qualification for it. They do say if you're doing any modular course, you do need to report your performance for each module in detail, which means UMS performance for if you are doing a modular AS. So that's in Cambridge's own words, but most people won't be doing those, won't be doing that like structure of qualification.
All right, good. So yes, we have a recording of the webinar. Is it worth printing out the answer book just to get used to line spacing? I think it's completely your personal choice, to be honest, I would say, if you want to, but that's completely up to you. Right, cool. So that brings us to the end of our webinar for today. I don't think there's any more questions, but it was great for you all to be here. Could you, if you're still here, write down what was something awesome that you took away from this webinar that you're going to go away and apply and be like, yeah, I'm going to use that over the next 6 months, over the next year to really boost my preparation. If you had to take one thing away, what would you say it was? So put it in the chat to us now. And problem planning before answering questions, doing questions 2 different ways. Somebody says, I'm glad you took away that you should problem plan, because I think that's the number one thing to take away. STEP questions are much more approachable using this methodology. Yes. If you want to learn more, get yourself booked on stepmaths.co.uk/year13-step or year 12-step. Can we get those put in the chat again if possible? So in case somebody wants to click on them, they can. How useful thinking about the limitations of the techniques used in the questions is. Thinking about STEP not just as an extra exam, but it's preparation for my degree, the P.R.O.F methodology, and actually read the question before attempting. The questions were, somebody had asked before which questions they were. Step 1, 2014, I think it was 2004, actually. And 2004, Step 3, 2008, and Step 2, 2008. Yeah, that's it from the whole Oxbridge Formula team. Thank you very much for joining. The team, I will see you on my call. Okay, thanks so much, guys. Take care. Bye.